general relativity step by step. Right, I'm going to consider Cartesian coordinates. Coords, that's just x and y. And I'm going to consider a particular gradient, which is the gradient of an electric field. So I've got G, it's covariant 1 and G2. G1, of course, is di phi di x, and G2 is di phi di y. So that's just an electric gradient. This is all classical. I'm not going to do any relativity on this. Could be potential and GRSS. And I've got a velocity field. V, that's a gradient, I guess, which equals V1, V2, which equals, that's just V1, V2. It's the directions of the components of the velocity field. And I ask how much work is required to move a unit charge at velocity v in the potential gradient pot grad g. Well, the answer is just g dot v, of course. Or at least it is in classical coordinates. I'm going to have to be a little bit more careful here. So g dot v. Well, if I talk about g dot v, that's just g, which way around is it? 1 v1 plus g2 v2. It's just an ordinary dot product. But now I'm armed with the summation convention. So I would write sigma over I, gi vi, which equals just gi vi, because the summation symbol is assumed. Well, that's quite nice. And of course, what I want to do is to figure out what this answer would be in the barred coordinate system. So what is the work in the barred coordinate system? Okay, and the barred coordinate system is, of course, this kind of h theta one here, and it moves around. And so that's great. So what I want to do, of course, is to transform this beast here from Cartesian coordinates into a barred one. And what? Well, let's just try it. Vi. Let me just write out what gi is in the barred coordinate system. Well, let me give you the transformation law. So it's sigma over j. G, we're going backwards, I guess, but it doesn't matter. I, j, di by di x, x. Now, that's summed over j, so j is repeated. J is downstairs, so it's upstairs here. J has got a bar, so it's got a bar there. That I must be that I there. What about vi? Sum over j. Oops, I wrote g again. V bar j. I know, you see, I've got it wrong straight away. This is a superscript because this is a contravariant, or these are the contravariant components of a tensor. So I need to make sure that that I appears upwards there. I could do this just by looking at my previous screencast and figuring out what it was, but I think it's as well to derive it afresh each time. Right, now that i's on the upstairs, and so that I must contract with... I know it's got to be a j. See, there's quite a lot going on here. It's got to be a j because I'm summing over j, and I'm summing over j to mean that when I'm summing over j, there's got to be one j on the top and one j on the bottom. Now that's got a bar, so that's got a bar. This I here must be this I here. And now that I've written it down, I can get rid of the sums. There we go. That's great, isn't it? So, I ask, what's gi vi equals what? Well, of course, I'm going to use these transformation laws. So here's gi is equal to gj bar di x bar j by di xi. Now, I'm gradually going to wean myself off writing the summation convention, writing the actual sums. So there's an implied sum across J here, which I scribbled out from here. V, so this one here, what was that one? That was Gi for the gradient. And here's my vector, which is V superscript I. Bar J, di x I by di x bar J. There it is. Equals Gj bar Vj bar di x bar J di xi from here times this coordinate thing here, I over di x bar J. Right. Now, let's just have a think about what this beast is here. This is summed over I. Yes, it's summed over I because there's an implicit sum here. So this is summed over J. I'm getting myself tangled up here. That I is this I. J. There's two J's. I see what I've done. It's so easy to do this. And I'm going to leave this mistake in. Normally what I'd do is scrub this screencast and start again. But I think it's important. It's this kind of error here that shows the right way to think about it. And the fact that I've made this mistake shows that it's kind of obvious to do. I've got a J. The reason I noticed something wrong was the summation convention is always in pairs. And here I've got a J there, and a J here. Oh, and there's one there as well. So I've got 4. And normally you only have 2 at a time. So what I've done is I've abused my notation because I've got a J here and a J here, and a J there and a J there. And it's a different beast because if I put the summation convention back in, let's just write out this thing again. It is, in brackets, sigma over J, some stuff with J's in it, di x bar J, di xi, times, now look what I wrote down, sigma over J, V bar J, di xi by di x bar J. That J and that J are both what you call dummy indices. It means that we could put J equals 1, 2, 3, however many dimensions you've got, 1, 2, 3, 4, 5, doesn't matter, 1, 2, 3, 4, 5, J. But bringing them together, I'm using the same symbol for both, which is kind of a tactical error. As opposed to this I here and that I there, these I's are legitimately the same one because those I's are summed over here. So implicitly there's a sum over I here, which I didn't even bother to write down because that's the summation convention. But I made a mistake by writing down the same dummy index for both of those. So I'm going to have to redo that. Sigma over I, I'm going to leave this one, sigma over J, G, J bar, di x bar J, di xi, sigma over K, let me just write it down, that's going to be K, di xi by di x bar K. So what I've done here is all I've done is route out the formula again, but I've changed the summation variable from J, which was interfering with this J, which was confusing me, and I've written it down in K again. And now I've put the summation convention back in. I've put the explicit summation sign in, which of course I don't need to do. Einstein's summation convention is now satisfied because I've got a repeated index I, one there and one there. One's on the bottom and one's on the top, so that's cool. And we've got 2 J's. We've got a J there, and we've got 2 K's, one there, one there. All I'm going to do now is use the Einstein summation convention, and then I can start fooling around with things. AJ bar, just writing it down, di x bar J by di xi. V bar K, di xi by di x bar k equals, oh no, it's called an A? No, it's G. I've written an A. It's a gradient. G, J bar. And remember, implicit summation over J, which is there and there, over K, which is there and there, and I, which is here and here. That I summation being the original summation in the dot product. So it's as well to be clear about what you are summing over and why you're summing over, but Einstein's summation convention makes everything so much nicer. V bar K, and remember this is just G, J, V, I, V, I, summed over I, which I don't need to say. Times all the other stuff. All I've done is written that down there, this down here. What's left? Di x bar J by di x I by di x bar K. Right. I'm going to put the summation convention back in. G, J bar, V, K bar, sum over I, di x bar J by di x I by di x bar K. What's this thing here? Well, it's not as bad as it might look, because what we've got here is two Jacobian matrices, but one the inverse of the other, as I showed in screencast, whatever it was. Well, let me write it out. We've got di x, it's a piece of magic, this. It really is a piece of magic. Once you get this, the whole of relativity just falls out. Once you've got this, di x bar J by di x1 by di x bar K, plus, I'm doing the summation over I, di x bar J by di x2, because we had a 1 here, and now I've got 2, times di x2 by di x bar K. That's a 2, not a 3. 2. Plus all the other terms. Equals di x bar J by di x bar K. Because what I've done is I've decomposed the equivalence of di x bar J. I'm writing it in terms of how it changes with respect to x1, x2, x3, x4 and so on. So all that is a restatement of my original law, which is that di f equals di f di x1 delta x1 plus di f by di x2 delta x2 plus dot 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 plus all the other dependencies. Okay, so I've got this thing left here. Do you see how all that collapses down? This is quite a complicated beast. We've got a product of partial differentials summed over I, and you think, oh my goodness me, that's a terrible mess. And all it is this. Equals 1 if J equals K, and 0 otherwise. Two ways to see that. The first way to see that is that we are multiplying together the Jacobian matrix and its inverse, so we're getting the identity matrix. The other way to see it is just by thinking about it. So what's di x bar 3 by di x bar 4? Well, that's going to be 0, because when we change x4, we don't, by construction, when we change x4, we leave all the other variables alone. What's di x bar 3 by di x bar 3? Well, that equals 1, because when we change it, we change it. So this beautiful little thing here is just a 1 or a 0, depending upon whether j equals k or not. And if it does, it's equal to 1, and if it doesn't, it's equal to 0. So where does that leave this formula here? Where does that leave my little formula? Here it is. Got a bit sidetracked, but I'll go back here now. So we've got GIVI equals GJVK times this thing here. Actually, now is a good time to introduce this symbol. That's equal to, well, now I've talked about it. Di x bar, of course, it's the same without the bar, equals delta jk equals the Kronecker delta. write that out again. Delta. Kronecker, very famous mathematician, equals 1 if j equals k, 0, j not equal to k. So if you take that as the row and column of a matrix, it's just the identity matrix there. So that's the way of expressing it. Kronecker delta has always got one up index and one down index. I'll come back to this in a minute. So I'm just going to rewrite from here my expression. What have we got? We've got GIVI, zoom in a bit, GIVI equals G, now what letters did I use? J and K. J bar, K, no, it was VK bar, times delta JK, where this thing here is the Kronecker delta. Okay? Now, I'm casually using the summation convention. So it's really summed over J and K, G, J bar, V, K bar, delta, J, K. But you can see, if J is not equal to K, this just drops out. So I'm really taking the sum over, let's say, L, G, L bar, V, L bar. Because this guy here is killing, this kills anything where J is not equal to K. So all the off-diagonal elements just disappear. So we're left with just the places where J equals K, so I may as well give it a new letter, and I've called it L. And by the summation convention, it's just GL bar VL. GI VI equals that. Oh no, there's a bar there. That's quite a lot of work. But what it basically means is that I can take a product, an inner product of a covariant vector, or a vector written in covariant form, with a vector with contravariant components, and it doesn't matter what expression or what coordinate system I use. So GIVI equals G, I'll call it L, V bar L, which tells me that G1 V1 plus G2 V2 plus G3 V3 plus however many they are, you might be working in a 15-dimensional space, G15 V15 equals G bar 1 V1 bar plus G2 bar V2 bar plus dot 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 plus G15 bar V15 bar. So what you do is you say that GIVI is invariant. It does not depend, this quantity does not depend on the coordinate system used. Isn't that wonderful? GIVI, one subscript down, one subscript up, implicit summation over I. This thing here, the dot product, which equals that, does not care what coordinate system you use to get those components, because it's equal in each case to the dot product of G as a vector in its own right, as an arbitrary vector, with V. And so when you extract the components, G1, G2, G3, they depend on the coordinate system that you use, because these guys are different. G2 bar, G3 bar, they're different. And these components change when you move from one coordinate system to another, but the dot product does not. That is why the dot product is useful, because it does not care how you describe it. It's got meaning in its own right, that is not tied to how you choose to describe it. That is why it's interesting. That is why it's useful. And the fact that I can write that down and understand that there's a summation, an implicit summation over I, tells me, or it's a symptom of the beauty and power of the Einstein summation convention. Actually, this went on far longer than I intended to, so I'm going to stop right there.